All right, hello again, everyone. So today we are going to talk about chapter 4, which is linear programming, and we will see an algorithm for two-dimensional linear programming, and we will see a different uh, algorithmic technique today, which is randomized algorithms and finding incremental solutions. So yeah, today's topic will be something different than plane sweep. So we have been seeing the plane sweep algorithm for a number of weeks now. But today we are not going to talk about plane sweep. We will talk about an incremental randomized algorithms. And in randomized algorithms, we are going to see that the important thing is the um, expected running time. So it's the worst case. The worst case of the algorithm that we will design is going to be O(n) square, but the expected running time will be O(n) linear, which basically tells that with very high probability we will always see a linear running time algorithm, which is going to be very efficient. So it will be the observing the worst case will be almost impossible. Only a certain permutation of the input will lead us to a worst case, and we will try to avoid this single or a number of permutations out of trillions of such permutations by randomizing our input as the first step. So there's actually nothing uh, fancy about randomized algorithms. The only thing that is important is whatever order the input is given to you. If as the first step of your algorithm you randomize the input, or you randomize the order of your input elements in an incremental algorithm, you basically create a random permutation, and this random permutation's expected running time will be linear, and you will not face the O(n) square worst case running time. So today's topic is about that. And the motivating problem is manufacturing with molds. It's like a three-dimensional problem, but we are going to formulate this problem. When we analyze this three-dimensional problem, we'll see that what we have is actually a two-dimensional problem. It's actually still a three-dimensional problem, but it will be a two-dimensional linear program. And actually, a two-dimensional linear program will also geometrically, it will also be a two-dimensional problem. We will try to find out intersection of half spaces, half planes in 2D, intersection of half planes, and we will just be looking for a certain point in this half plane, and therefore we will not be looking for the actual intersection area of these half planes. But let's see what I mean by these half planes. All these things are really abstract right now, but it will become clear as we go through over the lecture topic by topic. All right, so actually I want to first start talking about the motivating problem in 2D to make things clear. In 2D, the counterpart of this problem is going to be a one-dimensional LP. But let me just try to describe the problem to you by drawing a 2D version of the problem, and then we are going to extend this to 3D, which will give us a 2D problem at the end. So the 2D version of this, when we try to solve it geometrically, we will see that we have a one-dimensional problem. Okay, so let's bear with me, and I hope you will understand what the problem we're trying to solve in a couple of minutes. So the manufacturing with molds is this problem. Imagine you want to manufacture a certain shape. In this problem, we are going to limit our shape in the two-dimensional version. We limit our shape to polygons. Imagine we want to manufacture polygons. Imagine we are a toy factory, or imagine we try to manufacture keychains, plastic keychains, and they are two-dimensional entities, and they are polygons. Now, our goal will be to create a mold for this. So these are plastic. So what we will do is we will just melt the plastic and put the melted plastic in a mold. Okay, so a mold will be something that doesn't, I mean, it's solid, and it's not going to melt. Its melting temperature is much higher than that. In reality, for example, molds may be made out of concrete or some steel, some metal steel molds we may have. Okay, a mold will just be, for example, if you want to have a mold for this, what we will do is we will just create a mold in which uh, it is like the, yeah, this shape is already in there, all right? And we may, so this part, for example, it may be difficult to pour in. Let me actually drive a different polygon to make it life easier. For example, imagine we have this as our keychain, okay? So if this is the shape, which is similar to the shape in the book actually, this is the two-dimensional plastic shape that we want to manufacture. And we want to manufacture from these plastic shapes quite many. All right, therefore we design a mold, and this mold may be something, a metal that looks like this. All right, a metal shape that is like this. So this is our mold. All right, so what we do is we pour the plastic in this 2D version. Imagine this mold is just something 2D, okay? And what you do is you pour plastic, the plastic part, let's make it red. All right, so this part is the part that we want to manufacture, and we pour it melted inside this mold, and after it solidifies, we try to get this outside the mold. So one thing that you can do is you can break the mold and get this plastic outside the mold. But what we want to do is we want to reuse the mold. We want to use this mold for multiple manufacturing of this thing. So we don't want to break it. So one way to get this plastic out of the mold without breaking it will be to pull it in some direction. Okay, after it solidifies, you just pull it out of the mold so that the mold can be reused by pouring in another melted plastic in it. All right, so that's the problem. So the problem here is actually uh, given a shape, any shape like this. For example, this one can be. Is it possible to design a mold in such a way that, and we will always assume that the top of the, so the in 2D the mold is going to have the top surface. Okay, the mold has a top surface that is something like this. Okay, imagine the mold is always the outside boundary of the mold is always something like this. And imagine, given any polygon, uh, what we are going to do is we are going to align one of its sides of the polygon with the top face of the mold. So there are multiple ways to put this polygon P. Imagine I'm given this polygon P. So I can have this face or this edge. Look at this edge of the polygon. I can have this edge aligned with the top of the mold and have the remaining part that looks like this. All right, so this edge is aligned with the top of the mold. Or I can have, on the other hand, I can also have this edge. For example, if this edge is aligned with the top face of the mold, you will just have to imagine how it will look like when it is rotated. Actually, I can do that myself, right? I can select this part, okay, and I can copy it, and the copied one, I can actually rotate it. All right, so transform tools, rotate. So I can rotate this thing such that this one is now aligned with the mold. Then I can transform it, move. Okay, now it may be something like this. As you can see, I may have to change the height of my mold a little bit because this doesn't fit in, but still I can have a rectangular mold outside it. flatten image. Okay, now this is another way I can have my mold. This time the top face is going to be sorry, let me change the pen color so that it shows that it's the mold. Okay, so the mold's top face, the part that are just around it, actually it doesn't have to be this, its width doesn't have to be this much. I can design a mold that is like this. All right, and now this is the top face. So I can actually have different choices by asking, okay, I can have this as the top face, this has the top face, each of them in turn maybe the top face of the mold. Then I may try to pour plastic in it, and I may try to, and this time the inside faces of the mold are going to be like this. Okay, because in order to have the exact shape that I want to have as my keychain or as my plastic to the toy, what I want to do is the inside faces of the mold has to be exactly parallel to the edges of the polygon that I want to manufacture. Now, if I choose this top face as the top face of my mold, now the question is, if you pour plastic in it, is it possible to pull in some direction? By the way, another thing is, you can try to pull this in any direction. For example, if you have a shape that is like this, a parallelogram like this, and if you design a mold for it, you cannot actually take it out by vertically trying to pull it out of the mold, because this face, as you can see, if you look at this face, this direction, when you try to pull in exactly upwards direction, this face is going to block the pulling in that direction. So in order to be able to pull in a direction, I can either need to pull in this direction or in this direction, but if I pull this direction, then this face is going to block it. But what needs to happen is that whatever the normal of this mold surface is, I can only pull it if I have certain angles with respect to that mold face. And in order to pull the plastic safely outside the mold, it has to satisfy this angle constraint for all of the mold faces. So I may be going a little bit fast, but I'm going to come to that soon. But just you understood the problem, right? I mean, we have a mold. We want to manufacture some kind of a meltable material. It may be plastic, something else, and we pour it in inside this mold. And our goal will be to take this object outside the mold with just one pulling direction. So if it can be pulled in, by the way, we are not allowed to do screwing. Rotation is not allowed. So in this problem, the only thing that we can do is pull in some plus y direction. So if this is the positive y-axis, if this is the x-axis, all right, so this pulling vector is going to have its y coordinate, whatever the pulling vector is. Let's have this vector indicate xp, yp to indicate our pulling vector. Yp needs to be greater than 0 because that's the top face of the mold. If you're not pulling upwards, it's not possible to pull the plastic outside the mold. So you have to pull it in some positive direction in upward y vector. And since we are not interested in the pulling force actually, therefore what we are going to do is fix this yp to be equal to 1. So if you're interested in positive pulling direction, why not just fix it as 1? What I mean is that the solution that we will be looking for, let me have the eraser and erase this part. Is this the eraser? Yeah. Let me erase this part. Now what I'm going to do is I'm going to show you what the problem now is going to actually look like. So I'm fixing, let's get back to the 4. Okay, so I'm going to fix the y direction's magnitude to 1 plus 1. And my goal is to figure out a pulling direction. So this is x is equal to 0 direction. If x is equal to 0, so this is the 0, 1 vector. If the pulling direction is this, it means that it's the 0, 1 pulling direction. So if you're just pulling it straight up, that refers to this 0, 1 vector. All the pulling directions in which x is greater than 1 are actually they're all going to be on. So even this one, since I fixed it to be 1, the vectors are going to end here. Okay, so this is 0, 1 vector. So if you want to show pulling in this direction, for example, it may, for example, be a 5, 1 vector. Or if it's possible to pull this out by pulling in this direction, it may be minus 5, 1. So we will be searching for, given a particular top face, if the top face of the mold is fixed, our goal will be to figure out, is it possible with this top face fixed, considering all the remaining faces and of the polygon, is it possible to pull the plastic outside the mold by choosing in some pulling direction? Okay, is it going to be, by the way, for this one, I think it's may not, this may be, the solution may be infeasible. I mean, if you select this one as the top face for this shape, it may be impossible to take the plastic outside the mold, even in any value of x between minus infinity to positive infinity. All right, so there may sometimes be infeasible solutions. For example, for this one, the solution may be the 0, 1 vector. If you pull in, if you pull in 0, 1 direction straight up, you will be able to pull this out. But for this one, for example, if you have a shape that is like this, and if this is the mold, as you can see, if you try to pull it straight up, it's not going to, you will not be able to do that. I mean, you may think that, okay, if I pull straight up strong enough, it should come out, right? No, but actually, when you're pulling straight enough, this force actually is canceled by this. Actually, the actual pulling force becomes in this direction. Okay, so here, if you try to find the solution, it will be a solution something like 2, 0. Okay, so this is going to be, so let's talk about how we can solve this problem in one dimension. Okay, so let's try to formulate the problem, and let's see what we have in terms of mathematically. If somebody gives you a polygon, and if somebody selects a top face of the polygon, so what we are going to do is actually we are going to try every possible top face of the polygon one by one, in order to, since we don't know how to select the top face correctly, what we will do is we will try selecting every possible top face of the polygon one by one, and then if one of them leads a feasible solution, then we will say that it's possible to manufacture this plastic with a mold. By the way, what the question we are trying to answer, given a polygon, is it possible to design a mold for it so that without breaking the mold, you can pull the plastic outside the mold with just one pulling action? All right. For example, it's impossible to create a shape that is like a sphere. All right. You cannot have a single mold. Because, I mean, even if you represent your sphere with piecewise polygons like this, if you have a sphere which is composed of, or something like this, if you have, for example, an octagon, or something, or hexagon, for example, octagon, whatever it is. If you have something like this, if you select this one as the top face, it may be impossible for this one. Selecting every one of its faces are equal to each other. If it's a regular octagon, for example, a regular polygon with 8 faces, each face is equal to each other. So selecting one of the faces will be sufficient to answer this question. But selecting this face, you may try to figure out, is it possible to pull this out in this direction, or you may try to look for all the possible directions between minus infinity and plus infinity, and we will see how we can actually search for these directions, the feasible directions. And for certain shapes, like this regular octagon, it may be impossible to manufacture a single mold so that we will manufacture it with a mold without breaking the mold, with just pulling action. Okay, so for certain shapes it's impossible. So our goal will be to figure out, given a shape, that's going to, our input is just going to be a shape. Okay, in the version that I'm telling you right now, it's a 2D version. We are given a polygon. In the original version of the problem in the book, which we will solve, obviously, it's going to be polyhedra. Okay, polyhedra is a shape, a three-dimensional shape, in which its faces are all polygons. Okay, we will be given an example in the book is right here. So look at this one. So this one you see here is a polyhedra. A polyhedron. Polyhedra is the plural of polyhedron. So this is a polyhedron, which means that it's a closed shape. It's just like an extension of a simple polygon in 3 dimensions. It's a shape, a closed shape, we assume it will have no holes in it, and our goal will be to figure out, given the shape, given the polyhedron like this, is it possible to design a mold for it? So that we can reuse the mold again and again without breaking it. Okay, so this is the problem of casting or manufacturing with molds. There are different names for this. So this is the problem we will solve. But let's first take a look at the 2D version. Then I'm going to jump to the version on the books. So I hope everything is clear up to now. Now what I'm going to do is I'm going to mathematically formulate this problem, and let's see what kind of equations we try to solve, what we get. Okay, so in order to do that, let me get a new mold and a new polygon. So let's assume, let's try to solve for this one. Okay, so this is my, I'm going to use again red for that. First, what I can do is, yeah, I can draw my mold. Okay, and this is going to be the shape. So this is our example shape that we want to manufacture. So I'm actually drawing the polygon as they are not touching, but in reality the red edges will be exactly on these black edges. Okay, so given a polygon like this, we can identify the polygon with its vertices. Let's get back to red color. So we may be given V1, V2, V3, V4, V5, and V6. Okay, so this is a polygon with 6 vertices and 6 edges. Now, let's think about a pulling direction now. Let's use the blue color. Okay. Now, the pulling direction here, when we try to pull something in some direction, you're going to, it's actually unknown. The pulling direction that we try to figure out is unknown, only its y coordinate is known. So it's something like the solution that we are trying to find is something, a vector like x1. Okay, we don't know what x is. We try to figure out whether it's possible to pull in this direction. Now, given a pulling direction, look at this direction vector. In order for this direction vector to be consistent with the edges of the mold, or let me phrase it like this: for an edge of the mold, for an edge not to block, given an edge, for that edge, if you want that edge not to block the pulling direction, what should happen? Each edge, as you can see, of the mold can be indicated, can be represented. Actually, the only thing that matters here is that it's the face, the direction that the edge faces. Okay. Now we can let's be consistent with the book, and let's see how those inside edges are represented, the vectors. The normal vector of the mold faces are facing outwards. Okay, so this is how they are represented. So I'm going to also, the mold, if you look at this mold, so this is the blue thing that I have drawn here was actually the normal of that mold. I'm going to use black color for that. So each mold face has a normal. Normal 1, normal 2, normal 3, and normal 4. Okay, so these inner mold faces are actually the important parts that will block or unblock a certain pulling direction. Now, given a pulling direction, an arbitrary pulling direction, for example, this one. Okay, so this arbitrary pulling direction, if you look at the angle between them, if the angle between this one and this one is less than 90 degrees, if it's more than 90 degrees, for example, this is the case where the angle between this N1 and this will be 90 degrees, and this is also 90 degrees. So I can actually pull in all directions in between these two degrees, that will be safe. So if the angle between the normal of this mold and the pulling direction is more than 90 degrees, so if I pull in this direction, or if I pull, for example, actually they have to be up, so the ones that are above are all towards this side. Okay, if the angle is more than 90 degrees, then this will block the pulling direction. So how can we figure out whether the angle between two vectors is 90 degrees or more? We can look at the dot product, right? In other words, if the dot product, if it's more than 90 degrees, I think it's going to be, so if n1, so what I'm going to do is, this is the thing that we don't know. Okay, so this is my vector x1. If the dot product of this one and this one, if it's equal to 1, it means I'm here. If it's more than 90 degrees, if it's like this, the dot product in between them, okay, it's 0 and 90 degrees, 0 and 90 degrees. The dot product in between them, if the angle is more than 90 degrees, I think it's going to be negative, right? So exactly, yeah, you're right. So if the dot, so it's just if they are facing in the same direction, basically, if this is pulling in another direction, if according to this normal, if what I actually want is that, so I don't want this to be equal to 1. So this was, and they're facing the same direction. If it's less than 0, what will happen is that this will block it. And if you look at this dot product, this n1 vector, what is n1 vector? If you know v2 and v3, if the vertices are known, you can actually form the edge. The edge vector in counterclockwise direction is v3 minus v2. If this is the edge vector, the normal vector of this edge is going to be, for example, if this edge vector is like ex ey, if the edge vector is given to me as ex ey, the normal vector of that edge is going to be in the direction minus ey ex. Okay, so this is, if you just reverse the coordinates and make one of them negative, it will give you a vector orthogonal to the edge vector. In other words, you will get the normal vector of this. So it's possible to get these normal vectors. So what we have ourselves is that if you know this normal vector, and if you look at the dot product of this, we have an equation that looks something like this. Minus EY, which is something known, X plus EX is less than 0. All these things are known. The only thing is unknown. Okay, this is what we get for a single edge. And in order a pulling direction to be feasible, it has to satisfy, it has to be not blocked by all of the edges. So all of the edges should satisfy these, and they will have different normals. So if I call this E1 and E1, the other is going to give me minus E2yx plus E2x is less than 0. So this should be satisfied too. Then minus E3, since this one is 1, 2, 3, 1, 2, 3, 4, 5. 5 edges that are not the top face. For all these type edges, I have equations that look like this. E3x is less than 0. Okay, if you look at these equations, if you try to think about what they define, in terms, they actually define constraints on what x can be. And these constraints are one-dimensional constraints. My search for x from minus infinity to plus infinity, initially the places where x can be anything initially. Each of these edges is going to tell me something. What is this telling? For example, this one is telling x is greater than some value, or x is less than some value, depending on which ones are negative, which ones are positive. For example, it will tell you that x is, these are just constraints that look like this. X is greater than 3, x is less than 10, x is greater than 5, x is less than 18. Imagine we have something like this. If you look at this, what it will do is, the first thing is telling me that x has to be greater than 3. So now my feasible space dropped to this one. The second one, x is less than 10. Now in the second place, I'm going to be looking at x in this region. Then x is greater than 5. Oh, then feasible region again became smaller. So what we are doing is, we are actually at each of these constraints are half lines. They are on the whole interval in a single real line. They define half lines. They define regions. And every time when I'm processing these, I'm intersecting them, because I'm looking at the intersection, because they need to satisfy, the pulling direction has to satisfy all of them. So therefore, I need to try to find an x which satisfy all these inequalities. And in the one-dimensional case, this is really simple. In linear time, all I need to do is, actually this can be solved in linear time easily. I need to go over all of my constraints. And writing a code for this is really simple. You start maintaining a minimum x and maximum x. Okay, that is feasible. Initially, you set minimum x to minus infinity and maximum x to infinity. If you have a constraint in the form as x should be greater than 3, you need to set, you just take a look at this. Is this greater than minimum x? Yes, it is. Then minimum x should be that one. You update your minimum x. If you have a constraint in the form of x should be less than 10, by the way, this greater than and less than 10, all of them should be less than 0, as you can see. Depending on whether this EY is negative or positive, you will get positive entities here. When it's negative, as you can see, all the x's here are positive. What I do is I multiply both sides by -1, which change the direction of these equalities. Okay, so some of them is going to tell you greater, some of them less, depending on the sign of these edges. But what will happen is that if it tells x should be less than 10, okay, then I need to update my max to this. So you just maintain a min x and max x, and you update them by going over. And in some of them, for example, x is greater than 5, I again update minimum x, but x is less than 18. Do I need to update max x because it was already 10? No. So some constraints could already be satisfied by the other constraints. So the intersection actually could be included in the other half space. So I don't need to do any modification. All right. So this becomes a one-dimensional linear. This is called a one-dimensional linear program. Why is it called one-dimensional? Because I only have one variable to solve for. And why is it called linear programming? It's called linear programming because we have constraints on these variables that are linear in the form that is like this: ax plus b is less than 0, or ax plus b is greater than 0. So these are just linear constraints. If you have constraints that are of this form, in which x is not squared or log or other functions are not used on x, these are called linear constraints, hence the name linear programming. Okay, and it's a one-dimensional linear program because we have just one variable. In the book, when we try to solve this problem in 3 dimensions, in which the objects are 3-dimensional objects, we will have equations that are of this form: ax plus by plus c is less than 0, for example. Okay, so this will become a 2-dimensional linear program because the pulling direction will be a direction in which it can change both in x, y directions. We will fix the z coordinate. Z coordinate will be the top, the axis that is going upwards will be the z coordinate in our case, and we will fix it to 1, just like here, and we will try to solve for x and y. So the 3-dimensional extensions to 3-dimensional will be very trivial. It will be the same thing in the normal vectors of the faces are going to be 3-dimensional vectors instead of being 2-dimensional vectors like this. And our pulling direction will be something like a 3-dimensional vector, which is like x, y, 1. All right, so this is, and we will see that solving the 2-dimensional linear program, we will be able to do that not in O(n) squared time, but in expected linear time as well. So this is solving 1D linear program is guaranteed linear time. Okay, as you can see, the algorithm that we developed was very trivial. Just maintain a min x and max x and go over all the constraints. By the way, this n here is the number of faces of a polygon, and the number of constraints you have is equal to the number of edges of your polygon minus 1, which is the number of vertices, or the same as the number of vertices of your polygon minus 1. So its order will be linear on the complexity of your polygon. And we try to do this for, as I said, for every face of the polygon one by one. So this is, right now we know how to solve 1D linear program with a simple algorithm in linear time. Now we'll see how solving the 2D version can be done in expected linear time too. Okay, are there any questions? Okay, by the way, if you look at this normal vector here, n1, it's exactly the opposite direction as the normal of the face of the polygon. Usually when we have a polyhedron or a polygon like this, its normals are facing outwards. So if you're actually using the faces of the polygons, not the moles, the equation we are going to have with the pulling direction will be exactly the opposite. Okay, in that case, okay, actually you should have corrected me. If the angle is greater than 90 degree, the pulling direction is bad, right? We want it greater than or equal to 0. So this is what we want for that pulling direction to be valid. But if this n1 is the reversed normal vector, in which it's the normal vector of the face of the polygon, then it will turn into something like this. So that's what we have in the book. So, but as I said, in order, but probably you got the idea anyway. So we want the angle between these two pulling vectors and the normal vectors in order to satisfy valid pulling direction, we just use a dot product of these two vectors, which gives us a linear constraint. That's the key. All right. So let's continue with the three-dimensional version then. All right, and we'll see how the same thing is formulated. Oops, I went to the beginning of chapter 3. Yeah, so this is chapter 4 that we're going. So here, as you can see, it also describes the problem with a two-dimensional projection of the same problem, but just think about this as a three-dimensional object, as in the figure here, and imagine you're looking at it from the side. And depending on if you have an object like this, choosing a certain faces as the top face will actually prohibit the object to be manufactured. If you have an object that looks like a screw like this, if you put the white face down, what it will do is it will be an infeasible solution. And by the way, I forgot to talk about this in our 2D linear programs. Okay, in a 2D linear program, there are three possible cases. First of all, when we talk about these 2D linear programs, in addition to these constraints in a linear program, there is also an objective function, something that we try to maximize or minimize. In our molding problem, the objective function actually is not relevant. We can choose any objective function we want, because out of the, for example, if it's possible to pull in this direction, or if it's possible in this direction, which one would you prefer? If both of them are possible, if it's possible to pull this out in both directions or in any direction in between them, in order to solve our problem, any one of them could be chosen arbitrarily. But in general, in linear programs, we try to maximize or minimize some linear function of our unknowns. For example, in this one-dimensional case, we may say that let's minimize x. Okay, when you say minimize x, what it tells you is that you want, if there are multiple positions available to pull from, you want to choose the one that is leftmost. This is what minimizing x means. If multiple solutions are feasible, choose the one which try to pull it leftmost. Okay, you can, yeah. So this is this is the objective function should also be given. And this objective function is minimize x. It can be, for example, minimize 3x, or minimize 3x plus 5, or minimize minus 2x minus 8. So it may be another linear function of these variables, of the unknowns. So it has to be also a linear function. We cannot say minimize x squared, for example. If we could do that, like, or minimize the absolute value of x, we want to have a pulling direction as close as to 0. We cannot do this. So this will not make it a linear program if the objective function is not a linear function of x and y. So if we have this objective function like this, as I said, we can actually select an arbitrary objective function for this problem. What it tells us is that this objective function, the coefficients that we have here, a and b. So if we have an objective function that is minimize or maximize ax plus b, it actually, this a and b, this ab vector gives you a direction. Okay, and you try to maximize this will give you a direction, and you try to maximize it in that direction. Okay, actually you're just not AB. It just gives the direction that you're maximizing. This B is not important, this constant. If you maximize this is something constant, so it doesn't change actually. We do not have constants in these objective functions, all right, because that constant will not change anything. No matter what you choose x, all the x's will have the same b with them, all right? So it doesn't change the objective function. So when we are minimizing or maximizing x, we just have a certain uh, direction in front of it. And in case of one-dimensional LP, it's going to basically say that you're either maximizing in this direction or in this direction, depending on whether this A is positive or negative, or whether you're minimizing or maximizing. So in 2D version, it will be an arbitrary vector that we try to maximize, and the solution of a linear program can be one of the three things. One of them, the first thing, is infeasible. So a linear program may turn out to be infeasible. Okay, what does infeasible mean? It means that these constraints are contradicting with each other. It's not possible to have an x. For example, imagine I added another constraint to this one. X is less than 2. Okay, can you select a variable x in which it's less than 2 and also greater than 3? No, it's not possible. These two constraints are conflicting with each other. In other words, the intervals that we are intersecting with each other, at the end, their intersection is an empty set. If the intersection of these intervals that we find out during the processing of these constraints, if it turns out to be an empty set, we call that linear program to be infeasible. It doesn't have a solution. Sometimes it may be feasible, but unbounded. The optimum solution may be unbounded. Okay, feasible but unbounded. This is basically the fundamental theorem of linear programming. What I'm saying is the result is one of these three things. That's one of the theorem of linear programming. It may be feasible but unbounded. The optimum solution may be unbounded. What it means is that, for example, if you just had constraints which only say x is less than this, x is less than this, x is less than this, and if you try to maximize, for example, 3x or 1x, it doesn't matter in our case actually. So x could be infinity in that case. So if this min x and max x is not bounded, if one of those constraints does not bound x in one direction, and if you're trying to optimize in that direction, you can make x as large as possible, and it will be possible to pull the object in that direction, and in that which means that we may have an unbounded. So it's feasible, but you may make x as large as you want, and it will satisfy all the constraints. Okay, in our case, it's not true actually. You can never have a polygon in the 2D version. I think it will not be possible to pull in these directions. I mean, x cannot be minus infinity or plus infinity, right? I mean, we cannot pull in these two directions. That's where x is infinity and here x is minus infinity. So in 2D polygons, this unbounded solution, we are not going to see that. But maybe in the 3D case, we may have. Or the third case is feasible but bounded solution. It may be feasible and the optimum solution is bounded, and this bounded optimum solution sometimes may be unique. Yeah, it will be unique actually when it's bounded. In certain cases, yeah, if our optimum solution coincides with an edge, actually there may be infinitely many solutions still. It may be bounded. There is also the case that the solution is bounded, but there are infinitely many solutions. Sometimes so that becomes the fourth case. It's feasible and bounded, and this bounded solutions can be a unique solution or an infinitely many solutions. If you have solutions, for example, on an edge, that will make it bounded, but in the 2D, we don't have it in 1D case again. Okay, so these are the possible cases of linear programming solution. So before going into the 2D version continuing, I think it's a good time to have a 15-minute break. Let's have a 15-minute break, and I will continue at 7:05 all right, see you all in 15 minutes. I'm going to stop the recording, and then I will come back at 7:05. All right, see you all.